Zoom. So today we have a speaker, Associate Professor Kai Puolamäki, who is from the Department of Computer Science, University of Helsinki, and also from the Institute for Atmospheric and Earth System Research, INAR. And he is also the Vice Director of HEAT. And then today he will be talking about robust methods for explaining classifiers and data. But before I give the floor to Kai, I will remind you that if you have some questions during the presentation, so please raise a hand and I will give you the floor. So Kai said that he can also accept some questions in the middle of the presentation, but of course then when he's finished, so then the floor is open for your questions. But please, Kai, go ahead.
Okay, thanks, Laura. So yes, so as you can see from the slides and from the chat, also you can see the slides via this bit.ly link, at least for a while. So I thought that it would be kind of nicer under these conditions that you can see the actual presentation. And then before I start, so thanks for introductions, and then I will now try to change the slides, which I succeeded doing. So then what I'm going to present is a joint work with Andreas Anton Björklund, Andreas Henelius, Emilia Oikarinen, and Kimmo Kallonen, and we have a paper published last year, which you can see on the screen. And we are also, continuing this work, so there is a longer version under review, etc. But so this is, source for the technical contribution in this talk. Additionally, I thought that I will tell a bit about this topic more in general first, and then I will go more deeply in this technical contribution. So the idea of the talk is that I thought that I will first briefly describe what I'm doing, and then I will kind of then go to motivation in this paper and in this explaining classifier topics in general, and then I will kind of describe more technically what we have been doing, that what is the algorithm that we have been using, and what is robust regression, and what are explanations, and then I will conclude, and hopefully this will last about half an hour or so. Okay, so I have a small group at the Department of Computer Science and shared with INAR, and my research topic is generally to develop computational methods using machine learning and artificial intelligence, especially to analyze problems related to physics and quantum chemistry or chemistry together with substance area experts. And then kind of the keywords that what kind of characterizes what we are doing is how to visualize, explore, and understand the data in interaction with the user. The user could be, for example, a physicist or some other person who is trying to understand the data. And then the data that we have been using, might be from the measurements, physical measurements or simulators, and then we are using all types of artificial intelligence models. So in this work, classifiers, and then one other keyword for our work has been that how to do this in a statistically principled and robust manner. So this is important, especially, if you want to make decisions based on data. So of course there are kind of millions of possible patterns you might see, and then what are the kind of the really, and then it's kind of important to have some statistical guarantee of the fact that you are not just seeing some random patterns, but you actually, when you make decisions, or conclude something, so there is some statistical proof of that. So this is, kind of an overview of our group's kind of mission. And then, so then if you kind of summarize that what we are doing here, so we are kind of so if somebody is trying to make this super artificial intelligence that will rule the world, so we are not these persons. So we are kind of we are Okay, so now yes, so what we are kind of then doing is that we are trying to find ways of somehow augmenting artificial intelligence with human intelligence, or augmenting human intelligence with artificial intelligence, with the kind of the belief that this is the way forward. So this is, I mean, also kind of the one of the ideas behind this work. And I guess that, of course, I mean, in general, I mean, the kind of the interaction between the humans and artificial intelligence, so it is a very large topic, and this is, I mean, let's say one slice of this domain, so what I'm going to present here. Okay. So then if I will now go to kind of the motivation of this work, which is essentially explaining classifiers or supervised learning algorithms. So at simplest, what this means is that we have some process, like a training process, by which we learn a function f, and which tries to approximate some class, and then now our kind of and often, I mean, this could be some state-of-the-art classifiers, and often these functions are what you call black boxes. So it's difficult to understand what they are actually doing, and but for many reasons, I mean, it would be kind of very good to know actually why these systems work as they do. Even so, it is often not enough just to have a good accuracy, and there are kind of several reasons for this. For example, you want to kind of understand and trust the predictions or classifiers. So one of the original motivations for this, for the work that I'm presenting here, was in the domain of particle physics. Particle physicists use some deep learning models, some neural networks, to classify particle physics events that they observe in detectors, and to different classes. Basically, that is the particle jet generated by quarks or gluons, for example, and I have later an example of that. And for the physicists, it's not enough just that, I mean, the classifier appears to work fine, but it's also important to understand by which are the criteria by which the classifier makes the decision. So it's part of the understanding of the physical processes. And also, I mean, there are, as you know, so there are lots of kind of legal requirements that you must be able to explain many kind of explanations, that it's not just enough to say that you were not granted a credit, but and it is because some deep learning network said so, but I mean, you have to be able to explain that. So this is why kind of understanding these black box models and explaining why they make decisions, so it's kind of a very hot and important topic. And then so I thought that I will give a kind of a very kind of a, and then the question is that how to do these things, how do we explain the classifiers. And then I thought that I will give a very brief overview of how these model explainers do. So the starting point here is that we have some machine learning model, classifier in this case, and which has been trained by some process, and we assume that it is kind of so in this work. So then, I mean, so then if we want to explain what is happening there, so we can have kind of a black box dependent methods. So for example, the classifier algorithm can be kind of somehow understandable, and kind of or somehow the explanation methods can somehow depend on the classification algorithms. For example, for deep learning networks, so convolutional neural networks, there are some methods for explanations that are specific for these deep learning methods. For example, they somehow take into advantage some intermediate presentations within the networks. And the other option is to use black box agnostic methods, which basically explain classifiers, and they don't really care how the classifier works. And our work is kind of a black box agnostic approach, that our methods, I mean, basically works for any types of classifiers. And then there are two types of explanations, generally speaking, global explanations and local explanations. And our kind of approach are in these local explanations domain. And all of these methods work in a general sense in a way that we have the black box classifier, and then we somehow reverse engineer it, and then we kind of show some sort of a simplification of the very complex model such that the human can understand it. And now this interpretable simplification acts kind of a glue between this very complex black box model and then the human, and hopefully it will lead to more understanding in the process. So then if we go forward with these different explanation types, so what are the global explanations? So the idea of the global explanation is that we kind of somehow try to make some sort of a global model that approximates the classifier globally as a whole. And there is long history of these explanations, so it dates back to 19th, and we had also have had some work on this topic some time ago already. So before explaining classifiers became very famous. But the idea here is anyway that we make some global model that tries to estimate the classifier as a whole. So this doesn't work if the classifier is, I mean, very complex often, but I mean, for some cases, this is a very usable approach. And then where we are put in is the domain of local explainability. So the idea in the local explainability is that we don't try to make a model of the whole black box classifier, but instead we are interested in a question that, okay, why is this specific data instance classified as it is classified? For example, why is this image of cat classified as it is classified? And then we obtain a locally interpretable explanation. And this is now the kind of what we are kind of trying to do. And okay. And then so what is now the main principle of how these classifiers or these explanation methods work? And in all of them, the idea is to somehow to perturb the data and see how the classifier behaves, because we are not kind of allowed to look inside the classifier, but we can evaluate the classifier. So if we can make smart perturbations, and then we can conclude something of the classifier. So here is one instance. So for example, you can probably now classify a picture as having a guy or not having a guy. And now if I kind of make these kind of three perturbations, so then I ask you that is this first picture a guy and second picture a guy, and this is how you respond. And now from here I can kind of conclude something of how your internal classifier works. And so basically what I found out here is that I mean, you are using probably this part of the picture to recognize my face, and this was kind of a nice insight. And this is, I mean, kind of some main idea of how all of these local model agnostic explanation methods work. That you somehow perturb the data and see what happens. And what they vary is that how to perturb the data and how to make the simplifications, etc. But this is the main idea. Okay, but one thing that I mean, one thing that is kind of now interesting here is that the key point is that how do you perturb the data? And one thing that people have been missing, and one thing that was kind of a motivation for us, was that actually how you perturb the data matters a lot. So here is kind of a simple example that I try to kind of visualize something that assume that we have two variables, two covariates, and assume that we have a classifier that has a local decision boundary like this. So it is going to so if you look at the decision boundary alone, so you would think that, okay, the parameter y is the most important variable, because I mean, if you go to the y direction, so I mean, the gradient of the decision boundary is this direction. But actually, if the data is not is in the direction of the x-axis, so then actually in practice, in practical sense, the variable x is actually now the most important in making the classification decision. And this is actually, I mean, what happened, what we noticed that happened in the physics example. So in physics, for example, the data is within a certain manifold. So I mean, all the kind of physically allowed data points can be observed. But when you train this deep learning classifier to classify these particle jets, so it doesn't, of course, know anything about the physical domain. And then if you kind of try to explain the classifications by using the classifier decision boundary alone, which the other methods do, competing methods do, so then you get kind of a non-physical explanations that kind of seem to violate some conservation laws, for example. And now one of our contributions is that we kind of actually take the distribution of the data into account. And this is not only what happens in physics or in natural sciences, but I think that always when the data is kind of in some manifold and the classifier learns the data, so then the classifier kind of takes the data manifold into account when the learning process, and you can't really decouple how the data is distributed and how the classifier is kind of model is kind of working. And here.
Sorry to interrupt. There was one question that was sent in the group chat. I don't know if you want to answer that now, or do you want to wait until the end?
Yes, I can answer now if it's not super long.
Alex Jung was asking that did you also consider personalized explanations that take into account different user background?
No. Yeah. Answer is very short.
Okay, good. So then you can continue the discussion.
Yes, And so here is another example that assume that we are kind of making a model of income, whether it is high or low. This is a kind of a toy example, and then we have a model that weighs education more than age. So if you have a higher education, you have a higher income, but also if you are older, you have a higher income. And now if you look only at the model, so it might seem that okay, the education is the most important attribute. But assume that we are now studying salaries at the university department where almost everybody has high education. So then, actually knowing that education is high is much more informative in the kind of deciding whether you have high or low income. So even if in this kind of very simple examples, so you can argue that the distribution of the data is actually very relevant for the explanations. And this was kind of one of the main motivations for our work, that how to take the distribution of the data into account when in explanations. Okay. And then so then what we kind of did was that we kind of then the question is that okay, how can you kind of take the distribution of the data into account, and how you can avoid this kind of random sampling of the data when making the explanations, because the other explanation methods basically sample kind of somehow random data points around the point of interest, and then they compute the gradients in various ways, and then you have this problem that you are not really data kind of you actually don't take the distribution of the data into account in the explanations. So what we did was that we kind of thought that okay, took a step back and kind of thought that what is this problem actually all about, and then we kind of decided to formulate this explanation problem as a robust regression problem. And this turned out to be actually, I think, a very nice approach in a sense that in addition to solving the explanation problem, we actually managed to make quite a competitive, robust regression algorithm. And because the computational formalization is quite general, so actually our kind of explanation method is actually a bit more general than some of our competition. And so this is, and I think that this was kind of a nice one of the nice things here, that actually we got also a good robust regression algorithm at the same time. So So then if I kind of continue here that, okay, then what is the robust regression and how does it relate to the explaining classifiers at all? So the robust regression means that we have, like in this example, so if we have some linear space of points, and then if we make some orderly least squares regression, so it can be if you have some outliers like these ones here, so the least squares regression, I mean, gives you kind of a wrong result, or at least it doesn't follow these kind of main bulk of the points. And the robust regression methods, the idea of them is that they somehow ignore these outliers in one way or another, and then they try to fit the data in a kind of find the actual relationship that is followed by non-outliers in the data. And there are some, I mean, this is an old topic, and there are, I mean, some works, different types of approaches to do robust regression. And then kind of what we kind of, our contribution is essentially that then we kind of proposed a new robust regression method that basically, where the idea is that we kind of find the largest subset, find the kind of given some, we try to kind of find this kind of a tunnel or pipe, which is shown here in kind of a violet color, that contains maximal amount of points in this regression problem. And this example is now one-dimensional regression, but of course, in actuality, we do kind of a multi-dimensional regression. So basically, the computational problem is that find a straight line such that as many as possible points fit into this kind of this pipe here, and then essentially the outlier points, they are then just ignored. And this is the kind of the computational formalization of this algorithm, which we call SLICE, sparse linear subset explanation algorithm. And then how does this relate now to the kind of the explaining classifiers problem? So the relation is that instead of having this for the y-axis, we kind of replace with the y-axis the kind of the prediction of the classifier. So let's assume that we have a probabilistic classifier that outputs some probability, and so we replace the y-axis with prediction of the classifier, and then we do robust regression on this kind of this covariate versus the classified prediction. And then one slight modification is that then we have some point of interest, which is shown here as an orange color. So now we want to make a local explanation for this point of interest. And then this doesn't yet look very local, but then if we make this pipe kind of, or this pipe through which the data has to go narrower, so then suddenly what we have is a local explanation. So essentially, we find kind of the largest subset of the data that kind of fits into this pipe, and now we have a kind of a local explanation. And you notice what happened here is that we didn't need to do any sampling of the new data points, and now we kind of automatically obey the distribution of the data, because I mean we are actually using samples of the data to do the explanation instead of trying to generate a gradient by sampling random data points around this explanation point as competing methods do. And this is now the kind of the basic idea, and then you just do this in many more dimensions. And additionally, we use sparse regression to have fewer non-zero covariate coefficients to have, I mean, more kind of to have kind of a simpler explanations. But this is, I mean, additionally one thing that we do, but essentially this is now the main idea. Okay. And this is now actually, this looks quite, is kind of, so then I thought that I will kind of quickly go through maybe some algorithmic kind of things, because there are also some nice algorithmic kind of details here that you might find interesting. And then I will show you some kind of, let's say, experimental results and images, and then I will conclude. And I think that also, I mean, we actually spent quite a long time here to kind of trying to find this quite simple computational problem that, I mean, solving of which kind of we can kind of solve this explanation thing. But I think that it was yes, it was kind of good. So it was a kind of a good idea to kind of think this a bit deeper that way. And then if I kind of now go to kind of go through some algorithmic details, so you can find the details in the paper. So here you have some formula. So basically we have if you know lasso regression, so then you have something that looks, we are optimizing formally something which looks very much like a lasso kind of regression cost function. And we have, with the exception that we have this kind of a term that we only include the points here in this residual term that are within this pipe of a given width. And we have basically two parameters, which is the width of this pipe, and then we have the lasso kind of coefficient that controls the sparsity of the model. And then I think that one of the algorithmically, so we showed that, I mean, this computationally this problem is NP hard, and it's also difficult to approximate. So we can't find an approximable algorithm in general case probably for this problem. So then we have to do some approximations. And then what we did was that we used graduated optimization, which is quite simple, that we have a parameter that which we call here beta, that when beta is infinity, so then we have kind of our original difficult problem, and when beta is 0, so then we have a very easy and convex problem. And now, and then what we do is that we kind of gradually decrease this or increase this beta starting from 0 until to some very large value, so that we kind of in a simulated annealing idea or sense, we kind of end up in a relatively good optimal of the original function. And now one of the, I think that the contributions in our paper is that we actually did some we optimized the step size in this optimization process by computing approximation ratios between different cost functions with different betas, and this was kind of important in practice if we want to have a fast algorithm, because, I mean, the optimization of the lasso function is actually quite slow, and then we want to minimize the amount of different optimizations. And by using this in a principled way and computing approximation ratios, so we were able to minimize the required evaluations for different betas in this graduated optimization process. So it contains some kind of interesting. Okay, so now I kind of lost my. Okay, good. Yes, and so this is now the algorithm here. Okay, and now after this algorithm done, so then we can actually show. So we basically we have two contributions here. So one is for the robust regression problem, which is kind of different from the explanation problem, and what we show here is that we actually perform very well compared to other state-of-the-art robust regression methods. So here this first experiment is about the robustness of the explanations. So which means that if we add noise, so if we have some clean regression problem, and then if we start adding noise, so at some point, so our algorithm is going to break, and when the algorithm breaks, so this sum of residuals goes up, and this breaking appears somewhere at latest like with the 50% noise. And then we have a couple of different noise models that people typically use in this robust regression genre, and then we can show that, okay, actually we break, we are, I mean, at least as robust as our competition generally. So we are actually very robust to noise, and in that sense. And also, then if we look at the speed of the computation, so we actually also the fastest, or almost equally as fast as our competition everywhere. So actually because of our optimization, so this is one of the fastest robust regression methods that you can find. And then in this figure, you use this competition, and at the bottom, the fastest one is the Lasso regression, which is not robust. So it is just for as a comparison. But these orange lines are sliced or as, and lower speed or faster algorithm is better. And you can see that we are almost always the fastest of these our competition. And okay, as I said, so our kind of initial motivation was to then to use the kind of the model for explaining classifiers, and now kind of the advantages of this method is that we are totally model agnostic. We can use any black box models, and we don't need any distance measure between the data points, or we don't need to sample new data points as our kind of the competition methods. And conceptually, this is now very simple. So we are just doing a robust regression with, let's say, a very narrow kind of a pipe or small subset of points. And now, because our method actually is quite robust, so robust that we can tolerate lots of noise, so this actually works. So so it's not certain if the other robust regression methods could have performed that way, because they are not as robust to noise. And so this way we can explain the individual outcomes. And here we have, I mean, some of the examples. So here is some from EMNIS data. So we have a convolutional neural network that is trying to explain why this number 2 is number 2. And now these kind of, from this explanation, so all of the attributes are the pixels. And so there are something like 600 or 700 pixels or non-constant pixels in the EMNIS data set. And now I think that here it was, I always forget, but I think that it was, these orange points are the points that kind of have a negative weight. So if there is something here in the kind of the orange section, so it means that it is likely not 2. But if there is something, but these kind of blue points or whatever is the color points mean that they have a positive weight. So these kind of support the fact that this is actually the 2. And then you can kind of imagine that it is kind of shows you the separation between 2s and, for example, 0s. And this is kind of how the explanations look like for this EMNIS data.
Kai, sorry, there's also one question again.
Sure.
from Alex Jung. So what algorithm did you use for LAD Lasso?
You mean the LAD Lasso? I don't know now. So it was one of our competition methods, I guess now. So I think that they were the algorithm that we used. I don't now recall exactly, but they were in some robust regression library. So I can't now answer exactly what, but I think that it was anyway some it was kind of from the library published by authors of these LAD Lasso methods, I think.
Okay, thank you.
Yeah, so I don't. Yes, and then kind of the other advantage of our method, because we depend on the data, so we can ask questions that for this EMNIS data, for example, that how does kind of this model separate, for example, 2s and 3s. So now if instead of having all of the EMNIS data numbers, so if we only take a subset of numbers that contains 2s and 3s only, and then we use the same model and we use the slice, so we then get an explanation as to why kind of what are the kind of the pixels that the deep learning network uses to separate 2s and 3s. And here we can see that kind of the output for this explanation, and we can see that if you can kind of maybe see outlines of a 3 in this picture. So this is also kind of because we take the data into account, so it follows that the distribution of the data actually affects the explanations, and it allows you to kind of ask specific questions that, for example, that how are some specific classes or subsets separated. Okay, and then about our competition methods. So they are kind of some, like LIME is, I guess, the most known. So it's from 2016 by Ribeiro and co-authors, and it's kind of the difference with us and the LIME and other methods are that we don't. They require some sampling of the data points, and they also kind of require distance measure, and they can't be used for images out of the box, for example, like our method, because I mean of some assumptions that they do. So the other methods typically require a lot more kind of pre-processing and thinking before using than us. And here is another example of the that we used also kind of the slides. You can use it to explain text. And here is now the example of our kind of original kind of motivation. So how to explain the physics kind of physics experiments. And what is happening here is that we have here simulated particle jets. So you have a collision in a particle collider, and then you generate either quark and gluon, and then this quark or gluon kind of decays, and it produces a jet of particles, and this jet of particles is detected by the detector. And now we don't detect quark or gluon, I mean, directly, but from the shape of the jet and other properties, we can kind of infer some probability of as to whether it was a quark or gluon. And the physicists, they typically use some deep learning methods, for example, to do this classification. And then now if we run the slice, and basically this is how they do it, is actually that they kind of took a photo, they look at the jet directly from the center of momentum, and then they kind of make a picture. So it is essentially kind of an image recognition problem that, I mean, you can think that, I mean, when you see two-dimensional distribution of different particles with different energies. And now if we run the slice and try to explain how these deep learning methods work, so we notice that actually the quark jets are typically, I mean, more narrow, and gluon jets are more kind of widely spread. And this is actually what the deep learning method is doing according to the slice. So now we see that the jet is probably a gluon jet if it has kind of more stuff at the kind of the periphery, and it's more likely a quark jet if it has kind of more stuff at the center, which, I mean, makes sense from the physics perspective.
Sorry, Kai, there's again comment from or question from Alex Jung. Can you please show again the text explanation? What was the prediction that has been explained?
Yes, so the prediction, we tried to estimate some, I think that we tried to predict sentiment here, and whether it is a good or bad sentiment. If I kind of but the point here actually was that that LIME, which is our competition, so why I showed this example here, is that it uses the word street as one of the explaining words, even though it is very rare, so it is actually not very informative. But I think that this was kind of a sentiment recognition that you have enjoy, fun, great. I mean, these are kind of positive sentiment things.
Okay, great, thank you. And please remember that you can raise the hand by taking the mouse on top of your name there. So if you want to ask the questions, you are allowed also to ask the questions aloud during Kai's presentation.
Yeah. And and I guess that's also one of the pedagogical reasons why we also had this example in the paper is that, I mean, actually also for it's not just physics, but also if you do text classification or sentiment classification, so then actually, I mean, the data also matters, and not only the classification model, which I think was support vector machine in this particular example. Okay. But I think that that was kind of what I had to say, and I mean, you can find the code and everything in GitHub, and it's open source. And yes, so I think that, well, I think that so that was it, and so I guess as a summary, so. So I think that the nice things, take-home messages here is that, so this is an explanation method that actually uses the distribution of the data to make the predictions or make the explanations, which I kind of argue is important to understand, and that we were able to make this because, I mean, we actually formulated the whole problem as a robust regression problem, and then we got a nice robust regression problem, and as a bonus we got also a kind of a explanation method, or vice versa. And conceptually, you can see the concept in this picture. So the concept is actually quite simple, I think. But okay, thank you.
Great, thank you, Kai. And there was also, before I open the floor for next questions, I can also read Anton Björklund's reply for the question about the LAD lasso implementation. So it was from the MTE library for R, was the answer for that. But we still do have few minutes for questions. So are there still more questions from the audience? Okay, so there is again written questions. So please, you are also allowed to say the questions aloud, but of course I can also read them from here.
I have a question.
Yeah, please.
So what kind of data you use it for testing these algorithms?
Well, I mean, in this particular work, so we used, of course, some artificial data, especially for scalability and robustness, and I think that I think that the data sets mostly you could see presentations. So we are using kind of some EMNIST data, and then some text databases. So this is, I think it was IMDb data set, and then we use some physics data sets, and the physics data is provided by the CERN CMS collaboration. So essentially, the physics data is from kind of particle physics simulators that kind of simulate these experiments. So these are, I mean, the ones that we have been using for this paper.
Okay, more questions from the audience? So then there is again one written one. So how would you choose the width of the pipe in a multivariate case?
Yes, so I guess that with kind of so what we did is that, I mean, we can kind of experiment that if we can start with a very wide pipe, so then we have a lasso regression, which is easy, and then we start making it kind of narrower, and of course at some point everything breaks down when you have only a couple of points in the kind of the explanation, but typically, I mean, then you can kind of determine the width. I mean, depending, the width kind of defines how local your explanations are. So it's partially really a parameter of the model. It is kind of the choice of the user. So how local can you get? But I guess that kind of the sensible way to do that would be, I mean, have a sequence of widths, and then, I mean, choose the kind of the detail level that you kind of find most appropriate for your task. Of course, then you can use some rules of thumb that, I mean, what is the variance of the data, and try to kind of make an educated guess based on that also.
Okay, thank you. Still time for one quick question if there is.
if there are no others, it seems that I cannot raise my hand because I seem to be a co-host. So quick question is that, is there some evidence that the explanations are actually informative or explanations to people so that they help them?
Well, I mean, this is a very complex question. So what is not reported in this paper, but actually in the journal version, is that we have computed some kind of metrics for the explanations like consistency and things like that, and we are kind of performing well in that sense. But I mean, so now, I mean, of course, this question is, I mean, very kind of also ill-defined, that what is kind of useful. So I think that for physicists, it was useful to know that the kind of the regression, the classifier that they used, so actually they didn't do anything totally stupid, that what the classifiers did was somehow consistent with what they assumed. So I guess that in a sense, it was useful for them in that sense.
And I think this question is not specific to your work, it's for the whole genre,
Yes.
but it would be a really important question.
Yes, I totally agree. But luckily, I mean, lately, so in the work, so people are trying to evaluate also these aspects first by there's already some computational metrics to evaluate the goodness of explanation, and also, I mean, then maybe doing some task and actually whether it really helps in some concrete tasks. So this is, I mean, a very interesting question.
Yeah, thanks.
Okay, great, thank you. Now it's 1 minute past 10, and at least I have to run to the next meeting, and now fortunately the running is very short, but thank you very much, Kai. It was very interesting, and you had a great big audience here, and I hope I ask all the questions that were also written in the chat box. But thank you, Kai, and thank you everyone, and we will continue then next week. Bye bye.
Okay, bye.